Hello everyone. What we'd like to do in this video is discover a new type of coordinate system that turns out to be really useful in a lot of applications, specifically if we're dealing with circles or anything that has a kind of circle nature to it. So our entire life we've only really worked with one type of coordinate system. We've been very used to the rectangular coordinate system. So for example, we're used to plotting points that have x coordinates and y coordinates. For example, let's say we have the point 3 and 4. What this really does is it just gives us directions to a location in space from the origin. So we have some sort of origin, some place to start. Okay, we label this with the x and this with the y. And our directions are to move in the x direction 3 units. And then in the y direction, 4 units. So we can get exactly to a location. Again, by giving you a set of directions, how far to walk to the right or left, or how far to walk up or down. When we say positive, that means walk to the right for the x-coordinate. If it's negative, that means walk to the left. If the y-coordinate is positive, that means we walk upward. If the y-coordinate is negative, that means we walk downward. We just have a set of directions. Well, there isn't just one set or one way to tell you how to get to a point. How can I equivalently describe this location we're at, 3, 4, maybe using something different? Maybe, I don't know, maybe we could think, well, maybe if you were like an archer, let's say. You are an archer, and you are trying to shoot this location. You're standing here at the origin, and you would pull back your bow, and what would you have to do? You would have to first stand right here, and you'd have to aim upward to get to this location. So the first thing you want to know is, how far do I have to aim forward? How far do I have to go up so my bow is pointing right at this point? And then the question is how do we get to that point? You can think, how far do I have to stretch out my bow? How much power do I have to give it to get it there? So what would the archer want to know? It would want to first know, hey, how far do I have to rotate so we're pointing directly at the point? And then once we have that rotation, how far would we then have to go out? Here we can see we can have a set of 2 different parameters that can tell us exactly how to get to a new point. What would you want to know? Well, you would want to know how far to rotate. You would just want to know an angle. But if I just tell you an angle, well, that's really just telling me, hey, anything along this line. Okay, if we're at this angle. Okay, well, how far do I go out? Well, you just have to tell me a distance. How about that distance we call r? So what I've hopefully just introduced to you is a different way to think about how to get to a location. We call these polar coordinates. So right here, this is what we call traditional rectangular coordinates. But we can see there's another way to write this. We can use this, we can do something that's called polar coordinates. And we can instead, I can have to give you 2 pieces of information. Well, I'd have to tell you how far to go out. Or how about I have to tell you a certain angle to rotate. We usually put that in the second spot. And I'd have to tell you how far to go out. Or you could say, you have a certain length that your arm can go out, and then you would want to know, okay, where do I stop my arm from rotating? So you give a radius and then an angle. Or you could give an angle and then a radius. Either way, we are describing a unique point with these 2 parameters. Okay, so what we might ask ourselves now is what would this point be in polar coordinates? Well, we can actually figure that out because with this nice polar coordinates and this rectangular coordinates together make a triangle. So if we kind of put a right angle right here, let's try to think about what this radius here will be. Well, we know a little bit of information about this triangle. We know that the distance from here to here, well, this distance here is 4. And this distance from here to here, well, this distance is 3. So if we want to figure out the radius, well, we can just use the Pythagorean theorem. So here we would have that the radius squared would be equal to what? 3 squared plus 4 squared, or the radius would be equal to the square root. Okay, it looks like this radius for right now should make sense for the radius to be positive. Okay, this will be 3 squared, so that'll be 9 plus 16. This will be the square root of 25, which is 5. We could have recognized this was a 3, 4, 5 triangle, but I think it's nice to kind of see in general how you would maybe convert between the two. So we know that the radius here is 5. Okay, but now we need to know we have an arm length of 5, but now we have to know how far to rotate that arm length of 5. Well, let's try to figure out this angle here. Okay, well, we could use any one of the inverse trig functions. Since we know all 3 sides, we could use arctan, arccosine, or arccosine. We'll find out that it's usually fairly common to use arctangent, and I'll talk about that in just a second. There's a reason why you usually will use arctangent to find the angle. Well, that's because if you're converting between rectangular coordinates and polar coordinates, they tell you you know the x and y coordinates, so you would essentially know the adjacent and the opposite side. So in a lot of textbooks, when you're converting to angles, they use tangents because you know the x and the y, you know the adjacent and the opposite. So theta here, we could say, or we could at least say that the tangent of theta would be the same thing as 4/3. Okay, so we can figure out what this angle is by doing the tan inverse of both sides. Okay, let's use our calculator. Okay, now let's do it in degrees for right now. Maybe we'll do it in both in degrees. Let's do the tan inverse of 4/3. So this is roughly 53.13 degrees, or if we want to put this in radians, this will be a little bit less than 1 radian. 1 radian is roughly 60 degrees. That's a great way to think about it. Tan inverse of 4/3. Tan inverse of 4/3. We're getting roughly in radians. It's 0.927. So I know it'll be a little bit less than 1. 1 radian is roughly 60 degrees. So this would be in radians. Okay, so we could describe this point if we're using degrees. We could say this point has a radius of 5 and an angle of 53.13 degrees. To help us understand how to work in polar coordinates a little bit better, it's going to be convenient for us to find relationships between polar coordinates and rectangular coordinates. So what we want to do is we want to write down some relationships between x and y and r and theta. I'm going to go ahead and draw a picture, and we're going to write some relationships up on the board. Now, if you forget these relationships, I highly recommend just always drawing a picture. So let's go ahead and do that. So let's say we have this point here. Okay, in rectangular coordinates, we'd have an x and a y. Okay, so that means that this length here is x, and this length here is y. If we're talking in polar coordinates, well, you would need to tell me an angle and a radius. So let's say that we know what the radius and the angle are. How can we go from the radius and the angle, if we know r and theta, how can we figure out what x and y are? So now we want to figure out what x and y are. So we want to find a relationship between r, theta, and x. Between r, theta, and x. Okay, maybe I'll draw this picture. How about instead of putting y here, how about we put y right here? So we have a beautiful right triangle here. Okay. So if we want a relationship between r, theta, and x, this would be a relationship between the adjacent side and the hypotenuse and this angle, well, adjacent and hypotenuse, that reminds me a lot of cosine. So we'd have that cosine of theta is going to be the same thing as x over r, and we could multiply both sides by r. Can multiply both sides by r to get that x is equivalent to r times the cosine of theta. So we have that x is equal to r cosine of theta. Okay. And how about y? Can we find a relationship between r, theta, and y? Okay, so we need a relationship between, looks like the opposite side, the hypotenuse, and the angle. Well, opposite and hypotenuse reminds me of sine. So sine of theta is the same thing as y over r. So we could go ahead and multiply both sides by the radius. And we're going to get that y is equivalent to r times the sine of theta. So we have that our y coordinate is equal to r times the sine of theta, r sine of theta. Now this should make a little bit of sense here, because specifically, what if the radius was 1? If the radius was 1, that would tell you that the x-coordinate would just be cosine of theta, and the y-coordinate would be sine of theta. That's exactly what we discovered on the unit circle. Okay, now what about the other direction? What if we know x and y? What tools do we have at our disposal to be able to figure out what r and theta would be here? So we want a relationship between x, y, and r, between x, y, and r. Well, since we have this beautiful right triangle here, these would be the legs of the right triangle, and this would be the hypotenuse. So we'll have the Pythagorean theorem will be that r squared is equal to x squared plus y squared. Now, we could square root both sides. Maybe I'll write that. So we'll have x squared plus y squared. Now, I will put a plus or minus here. Now, traditionally, when we're thinking about a radius, we usually think about radius as always being positive, but we're going to explore here pretty soon the idea of, can we make sense of a negative radius? This is a great question to ask. Maybe it doesn't make any sense, but we're going to explore that idea and see if we can make sense of a negative radius. Okay, so I'll leave this plus or minus for right now. Okay, can we find a relationship between x, y, and theta? Between x, y, and theta? Well, this is opposite, this is adjacent, so I think we could say that tangent of theta will be equal to y over x. Equal to y over x. Now again, you could take tan inverse of both sides, but we're going to have to be very careful because we have to remember how tan inverse works. Tan inverse only spits you out angles between negative pi over 2 and pi over 2. And specifically, if it's going to tell you a positive angle, it's only going to tell you an acute angle. Well, it's possible for this angle to be obtuse, specifically, I guess, if we're in quadrant 2. So we're going to need to do actually a little bit more work when actually trying to convert from rectangular coordinates to polar coordinates. We're going to need to draw pictures and draw different right triangles, but we're going to do that exercise here in just a moment. So that's why I'm actually not going to write that theta is equal to the tan inverse of y over x, because we've got to be careful about how tan inverse works. So we'll just leave it how it is. But specifically, what I want to use here to try to understand what a negative radius might possibly mean is understanding that if we know r and theta, we know that the x-coordinate will be r cosine of theta, and then the y-coordinate will be r sine of theta. So let's plot a point and try to make sense of a negative radius if it doesn't make any sense. So let's first take a look at the point, I don't know, how about in polar coordinates, how about for r and theta? Let's say r and theta, let's say the radius is 5, and let's say theta is, I don't know, how about pi over 3? Okay, let's go ahead and draw this. So here is 5. And Here's 5. Okay, so we need a angle of pi over 3. So pi over 3. Here's pi over 4. I don't know. Pi over 3 is, I don't know, maybe roughly here. Okay, let's try to, it's hand drawn, but I don't know, a radius of 5, maybe roughly right here. So in polar coordinates, this length here will be 5, and this angle here is pi over 3. Okay, what would this look like though if it were in rectangular coordinates? Well, we need to remember that this is equivalent to r times the cosine of theta. That's what x is, and y is r times the sine of theta. So this would look like our radius is 5, so this would be 5 times the cosine of pi over 3, 5. And this would be 5 and the sine of pi over 3. Now you could use your calculator to figure out roughly what these are, but mainly what I just want to note here, okay, when I'm going to draw this is definitely not drawing anything to scale here. But that's saying that this physical length here, this will be 5 times the cosine of pi over 3. And this distance here, the y-coordinate, will be 5, and the sine of pi over 3. Okay, so that's this point right here in polar coordinates, 5 and pi over 3, and this is what it would be in rectangular coordinates. Okay, well, what if we change this problem, and what if it wasn't a positive 5, but it was a negative 5? So what if we put a negative here instead? Does this make any sense? Well, following the formula that x should be r cosine of theta and y should be r sine of theta, that means the difference here is I should have negatives on the radiuses. Okay, so that just means that if I'm plotting the x and y coordinates, the x coordinate would now actually be negative. So it wouldn't be 5 cosine of pi over 3. It's actually going to be negative 5 in the cosine of pi over 3. And this distance here, we need to go down. I should have given myself a little bit more board space, but I hope we get the idea. Then the y-coordinate would be going down negative 5 in sine of pi over 3. So our new coordinate would actually be roughly right here. Kind of a rough picture, loose picture here. But this is where the point negative 5 in pi over 3 would be if we're following kind of the directions of the conversion between polar coordinates and rectangular coordinates. So interesting. So in a way, a negative radius does make a little bit of sense here. What it means here is, well, the way I like to think about it is you're still going to be rotating an angle of pi over 3. Now, if it was a positive pi over 3, that means kind of go in the direction of the line that's touching the angle. So you'd be going this direction, you kind of going with the forward direction 5 units. If it's a negative radius, we're still rotating pi over 3, but instead of going in this direction 5 units, we go in the other direction 5 units. So rotating pi over 3, if it's a positive radius, go that way. If it's a negative radius, go in the other direction. So that's a way we can understand or thinking about negative radiuses. Pretty cool. All right, let's go ahead and plot these 2 points here in polar coordinates to get a feel for how negative radiuses work. Okay, so if we are rotating an angle pi over 3, so here's pi over 4, so pi over 3, I don't know, roughly here. Okay, this is an angle of pi over 3. Okay, if we were plotting the point 2, if we're plotting the point 2 pi over 3, we would go kind of with, or kind of, I don't know, going along the line that's touching the angle. So there'd be like, what, 1, 2, so we'd be roughly right here. But since it's a negative, this here would be the point 2 in pi over 3. I'm not going to go this way 2 units, I'm going to go backwards 2 units. So this point right here will be negative 2 in pi over 3. Okay, let's do this next one. Okay, so I have a negative radius and a negative angle. Okay. So we're gonna, instead of going counterclockwise pi over 4, this means we go counterclockwise. I'm sorry, we go clockwise pi over 4. Okay, so here's an angle of negative pi over 4. Okay, if it was the point 3 and negative pi over 4, we kind of go in the direction of the line that's touching the angle. So it'd be like 1, 2, 3. So this would be the point 3 and negative pi over 4. But if we want the negative 3, we go kind of we go in the other direction. So 1, 2, 3. So this is the point negative 3 and negative pi over 4. And that's how we plot points with negative radiuses. So one thing that's interesting about polar coordinates as compared to rectangular coordinates is that for a location in space, using polar coordinates, there's not a unique representation on how to get there. When we're using rectangular coordinates and we want to talk about a location, I tell you how far to go X and how far to go Y. There's a unique way to get to a location, or a unique way to give directions to a location using rectangular coordinates, but there are actually, we'll find that there is an infinite number of ways to represent a location using polar coordinates. Let me show you what I mean. So let's draw a picture. Okay. So here we have a point. Okay, it has its radius and it has its angle. Now this would be the nicest way to tell someone a point. You would say, hey, here is your radius and here is your theta. Now what would be nice is for you to report this with a positive radius and an angle between 0 and 2 pi. However, this isn't the only way to do it. This is the friendliest way to to tell someone directions to this point using polar coordinates. But what else could we do? Well, how else could we get to the same location? Well, if we're already right here and then we rotate an extra 2 pi, so here we'd be at theta plus 2 pi, well, it would be at the same location. This would be like, you know, if you were really mad at your brother or what. And you had to tell him directions somewhere, and you say, "Oh yeah, these are the directions," and then you'd be telling him to go around the circle a whole extra time. This wouldn't be the only way. You could have him also go, you know, if you were really mad at him, tell him the angle plus a 4 pi, or you know, a 6 pi, or anything like that. In general, you could have a radius, you could have your angle, and you could add any multiple of 2 pi, and you'd be at the same location. Where k is an integer, so k is can be what, -3, -2, -1, 0, 1, 2, 3, and so on and so forth. K is an integer. So here you would tell him at the location, and now you'd be telling him to go an extra way around, going counterclockwise, twice counterclockwise, 3 times counterclockwise. Be at that location. Now go clockwise. Now go around 1 whole time clockwise, 2 whole time clockwise, 3 whole times clockwise. Okay, but this isn't the only way we could do it. We don't just have to mess around with the angle. Well, another way we could, I don't know, maybe think about how to get to this point is with instead a negative radius. Okay, so if we have a negative radius, let's think about what this would look like. So right here, here's our radius, here's our angle. So now if we think about the point, this is the point r theta. This here is going to be the point negative r theta. So they're in different locations. But I can take this point right here, and I can easily get here. Let's see. Well, if we're at this point, a negative radius puts us over here. But now I can get back to the same location by rotating halfway around the circle. So go backwards and then rotate around half. You're exactly at the same location. So an equivalent spot here would be a negative radius, but then move this piece an extra pi. So this would now be, if we want to go, this would be a theta plus pi. So here's theta, and here's an extra pi. So if it was a positive radius, that would put us right here, but then now we're making it negative, that reflects us back there. You can think about it that way also. So we could also have a negative radius, take your angle, and you could add pi. But of course, then you could add any multiple of 2 pi to this. So you could add, pi plus another 2 pi, like 3 pi, or 5 pi, and so on and so forth. How about we just write this here for now? So this is another way to represent the same location, and here's another way to represent the same location. Okay, there's an infinite, and then add multiples of 2 pi to these angles from here, and you're going to be at the same location. So there's not a unique way to represent a location in polar coordinates, and that's one of the main differences between polar coordinates and rectangular coordinates. Rectangular coordinates has a unique representation of a location. Polar coordinates does not have a unique representation for a location. There are actually an infinite number of ways to describe a location using polar coordinates. Okay, so let's do a little bit of practice. Okay, so let's say we have the point 2 and pi over 6. What I want you to do is I want you to pause the video. I want you to plot this in polar coordinates. So this is an r and a theta. And then I want you to represent the same point. But give me another representation with the radius being positive, and give me another representation just with a negative radius. Go ahead and pause the video and give this a shot. Okay, let's do it. All right, so if we rotate an angle about pi over 6, this is roughly pi over 6. Pi over 6, here's 1, here's 2. Okay, so this would be the point, this here is the point 2 and pi over 6. Okay, we could get to this same point by just going from here and adding an extra 2 pi. So this would now be pi over 6 plus 2 pi. So what are we going to get? Another way to represent this point would be 2, and what is pi over 6 plus 2 pi? How would we write that as 12 pi over 6? So 13 pi over 6. Okay, here's another representation for the same point. What else could we do? Well, what if we had a negative 2? So pi over 6 and a negative 2, well, that would put us right here. Okay, so this would be the point negative 2 and pi over 6. Well, to go from this point back here, we could just add an extra pi. So pi over 6, we want to add halfway around the circle. So pi over 6 plus a pi, or 6 pi over 6, 7 pi over 6. So negative 2 and 7 pi over 6. So that's a way that we can take a point and write it in a couple different representations. Okay, let's now get some practice with converting between the two coordinate systems. Okay, let's first go ahead and convert from polar coordinates to rectangular coordinates. This is the easy direction to do it because there is only there's only one way to write something in rectangular coordinates. That representation is unique, so that's actually why I've given an r and a theta. If you're given an r and a theta, you're uniquely going to define x and y. Okay. So let's say in r and theta we have, let's say we have, 6 and how about 2 pi over 3. So let's convert this into rectangular coordinates. So it's really just as easy as knowing that x is the same thing as r cosine of theta, and that y is the same thing as r sine of theta. Okay, so the x is going to be 6 times the cosine of 2 pi over 3. Okay, if you don't have if this isn't a nice number on the unit circle, just use your calculator. Okay, but 2 pi over 3, I think cosine of 2 pi over 3, I think that's going to be negative 1/2. So this will be negative 3, and we'll also have that y will be equal to what? This will be 6 times the cosine of 2 pi over 3. Oh, sorry, sine. And sine of 2 pi over 3. Sine of 2 pi over 3, I think, is root 3 over 2. So this will be 3 root 3. Okay, so in rectangular coordinates, this is the same thing as negative 3 and 3 root 3. Let's actually verify that this at least makes some sense. Okay, I'm going to do a hand sketch here. Let's see. So what is this roughly? So what? Negative 3. What is 3 root 3 roughly? 3 square root of 3. So this is roughly 5.196. Okay, so let's do a sketch. It's a hand-drawn sketch, so it won't be perfect. Okay, we need to have a radius of 6 and an angle of 2 pi over 3. I'm going to kind of estimate 2 pi over 3. I don't know what 2 pi. Let's see. This will be what, 1, 2, 3. This is 3 pi over 4. I don't know, maybe roughly right here. This is going to be roughly an angle of 2 pi over 3. And we need to go out 6 units. So here's negative 6. And of course, this isn't going to be perfect, but I don't know. I don't know, something roughly right here. Roughly right here is going to be the point 6 and 2 pi over 3. Okay. So let's try to make an equal spacing here. 1, 2, 3, 4, 5, 6. So here is 6. And we can see here, look, if we drop this down, you know, it's hand drawn. But yeah, roughly negative 3 and 5.196. So this worked out great. Let's now get some practice with converting from rectangular coordinates to polar coordinates. Actually, in the beginning of this video, we actually did convert from rectangular coordinates to polar coordinates, but with the point I gave you, we are actually in the first quadrant. And it can sometimes get a little bit tricky if we're in a different quadrant, but I always just highly recommend that we draw a picture. So let's do an exercise. Let's say we have some point in the second quadrant. So how about negative 2 and 3? So this is something in rectangular coordinates. But let's convert this into polar coordinates. Okay, so let's draw our picture. Okay, so we're to the left 2 units and up 3 units. So here we are. So this is in, of course, rectangular coordinates. Okay, if we want this in polar coordinates, we want to figure out what this radius is, and we want to know what this angle is. Now, oftentimes when you're reporting something in polar coordinates, there's not a unique representation, which we just learned. However, when we're just going to be nice, we're going to be friendly, and to giving people directions, that we'll have the radius be positive, and if we're working in radians, we'll have the degree or the angle between 0 and 2 pi radians. If this was in degrees, it'd be between 0 and 360 degrees. Okay, so what I'm going to do is I oftentimes just like to draw a right triangle. Anytime we can work with a right triangle, we're going to want to work with it because we have so many great tools with a right triangle. We have this beautiful right triangle sitting here in the second quadrant. I'm going to go ahead and I'm going to draw it over here. But what I'm going to do is I'm going to think about this angle right here, this kind of acute angle, and we're going to call this angle here phi. So let's draw that triangle over here. So here's the angle phi. Okay, this physical length here is 3. This physical length here is 2. And we need to figure out what the radius is. That's the easy part. We'll just use the Pythagorean theorem. So we'll have that r squared is going to be equal to 3 squared plus 2 squared. So we're going to have that our radius is going to be equal to the square root. What is this going to be? 9 plus 4, or the radius will be equal to the square root of 13. We could do plus or minus. You could report this location with a negative radius, but we're going to be nice and we're going to report it with a positive radius. Okay, so we got that down. So we have a root 13 for the radius. Okay, what about the angle? Okay, well, I need to remember that tan inverse is only going to spit us out acute angles. Tan inverse only spits you out angles between negative pi over 2 and pi over 2. So it will never tell you an obtuse angle. So what do we need to do? Well, that's why I drew this phi here. But to figure out this theta, how are we going to do that? We're going to note that theta is equivalent to, well, going halfway around the circle would be pi. So how about we go pi and then go backwards phi? Okay, so all we have to do is figure out what phi is. Over here, we have that tangent of phi is going to be equal to 3/2. Or we have that phi will be equal to the tan inverse of 3/2. So we'll record that right here. So theta will be equal to phi minus the tan inverse of 3/2. Now, tan inverse of 3/2 isn't a nice number. So I guess what would the point be in polar coordinates if we wanted an exact answer? Well, you would write pi. You would write pi minus the tan inverse of 3/2. But how about we get a rough idea of what that is? So we can use our calculator. Let's make sure that we are in radian mode since I have a pi here. So mode, I'm in radian mode. So let's do pi minus the tan inverse of 3/2. So I'm getting that this is roughly 2.1559 radians. Okay, if you want to know what that is in degrees, I mean, I always just think that 1 radian is roughly 60 degrees. So, I mean, this is going to be, what, 60 and 60, so it's going to be something a little bit bigger than 120 degrees. So let's just check. So I'm just going to convert this answer into degrees. So I need to multiply by 180 and then divide by pi. And so this is 123.69 degrees if you want, if you feel better working with degrees. Okay, so let's go ahead and try another problem, or let's have you try one. I'm going to put a point in the 3rd quadrant, and I want you to write it in polar coordinates. Okay, so let's say we have the point. Let's say we have the point. How about -5 and -2? Let's say this is a point in rectangular coordinates. I want you to convert it into polar coordinates. Go ahead and give it a shot, and I want you to report it with the radius bigger than 0 and the angle between 0 and 2 pi. Go ahead and give this a shot. Okay, let's do it. I'm just going to draw a picture. Okay. Go left 5 units, go down 2 units. So this is where we are. Okay, this is in rectangular coordinates. In polar coordinates, we want to know what this radius is, and we want to know what this angle here is. Okay, well, I'm going to want to work with a nice right triangle, so I'm going to think about this right triangle right here, and I'm going to think about this angle right here being phi. So the angle theta is what we want. Well, how could we get angle theta from phi? Well, notice from here we could go halfway around the circle, so that would be pi, and then we would want to add. We would want to add phi. So that's how we could get to that angle. So that's why it's never the same. Kind of the formula for theta using a tan inverse will completely depend on what quadrant we're in. Okay, so let's draw this triangle. Let's draw this triangle. Okay, if I roughly draw this triangle, okay, this here is phi. This physical length here is 2. This physical length here is 5. If you want, we could rotate the triangle. Rotate this triangle. Okay, so this here is phi, this is 2, and this is 5. Here is our radius. So the radius is going to be equal to the square root of 5 squared plus 2 squared. So what will that be? 25 and 4. So that'll be root 29. Okay, so the radius will be root 29. Okay, and let's think about what phi will be. I'll write it here. Phi, or how about the tangent of phi? The tangent is opposite over adjacent, so that'll be 2/5, or that phi will be the tan inverse of 2/5. Okay, so theta is going to be equal to pi plus the tan inverse of 2/5. Okay, 2/5 is not a nice number on the unit circle, so this is of course this would be the exact answer. Pi plus the tan inverse of 2/5. Okay, but let's get a rough feel for what this number is. Okay, in terms of radians, I mean, halfway around the circle, this is like 3.14 radians. So this is going to be something, bigger than 3. So let's do pi plus the tan inverse of 2/5. Okay, and I'm getting roughly 3.463 radians. So this is 3.463 radians. If you want to convert that into degrees, we could multiply by 180 and then divide by pi. So that's roughly 198.435 degrees. Okay. So that's how we convert from rectangular coordinates to polar coordinates. All right, it's easy to go one direction when you're converting from rectangular coordinates to polar coordinates. When you're going from polar coordinates to rectangular coordinates, there's not much thinking you have to do. Just got to use the formula x equals r cosine of theta, y equals r sine of theta. But when we're converting from rectangular to polar does not have a unique representation. You're going to have to take a look at the picture, and then that's what I like to do. I draw the picture every single time, and I like to think about it. So that's my best advice. That's all I have in this video. What we're going to be doing in the next video is taking a look at what some familiar equations in rectangular coordinates look like in rectangular coordinates. We'll see that. Or sorry, what they look like in what equations. In the next video, what we're going to do is we're going to look at what familiar equations in rectangular coordinates look like if they are in polar coordinates. We'll see you there.